Hi, welcome to the next video on the Analytic Geometry series. So this time we'll be talking about hyperbola. So when we say hyperbola, something that you would see as two parabolas facing opposite with each other, but it's actually not. So it's like something like this. So that's hyperbola. And since hyperbola as one of the conics, it's actually made from the intersection of a plane and a double cone. So that's hyperbola. Okay, so this time we'll be talking about the formal definition of a hyperbola. So a hyperbola is a set of points such that the absolute difference of the distances from a point to a two fixed point to two fixed points called the foci is a constant. So that's hyperbola. Okay, so suppose this is our hyperbola here. And let's say this is our focus. First focus, second focus. So if you pick a point on the hyperbola, let's say here. So the difference of the distance from this to and the distance from here, the absolute difference is always a constant. So if we would like to consider this figure here, so I'll erase this first. So these 2 points are the foci. The point also here is the vertex, vertex 1 and the vertex 2. Now, an imaginary line segment connecting the two vertices here is what we call the major axis. In an imaginary line segment, an imaginary line segment, let's say we have another points here. So these points here are called the co-vertices of the hyperbola. So these points here, E1 and E2, the line segment connecting these 2 points is the minor axis. Hence, the intersection of these two axes, the major and the minor, is actually the center of the hyperbola, which implies that the center is not actually a part of the points on the hyperbola. Okay, there are two imaginary line segments that is parallel to the minor axis and passes through the vertices. So these are imaginary line segments parallel to the minor axis, passes through the vertices, is what we call the branches. So take note, this is the major axis. So this is the minor axis. So these imaginary line segments here passing through the vertices parallel to the minor axis are what we call branches. And there's also an imaginary line segment. There are also imaginary line segments parallel to the major axis passing through the co-vertices here. These are called conjugate axis. So they are conjugate axis. So the conjugate axis together with the branches form an imaginary rectangle. By that, we can create a line passing through each corner. So diagonal to the rectangle, passing each from one corner to the opposite corner of the rectangle. So let's say this is the line here passing from this corner to the opposite corner, and another imaginary line here. By that is where the lines to which the hyperbola is asymptotic to. So if you have a vertex here, you can create your hyperbola asymptotic to this line. So the hyperbola should be asymptotic to that. That's hyperbola. Okay, so from this, we denote the distance as A from, this is actually the measure of the line segment connecting the center to any vertex. So it's actually the distance from the center point to any of the vertices. So let's say we have the center and the vertex 1. So here, from here, it's measured A. We denote B as the distance from the center to any co-vertices. Let's say center to E sub 1. And we denote C as the distance from the center to any focus. Say, let's say, center to focus 1. That's it. Observe that your C squared minus A squared should always greater than 0. Why? Technically because, of course, the distance from the center to the vertex is actually lesser compared to the distance from the center to any focus. So as you can see here, unlike the ellipse at which the distance from the center to the vertex is larger compared to the distance from the center to the focus. This time it's quite different. They're actually, how to call this? It's different because the center to the vertex is actually lesser compared to the center to the from the center to the focus. That's it. Okay, so this time we'll be deriving equations of hyperbola. So let's consider again this. Let's say this is our hyperbola. Assuming my drawing is perfect. So these are the foci. These are the vertices. So let's say F1 as the focus 1, V1 as vertex 1, focus 2, vertex 2 and focus 2. The center. We have the co-vertices here. So from this we create a branch here, conjugate axis, another conjugate axis. So so these are my imaginary lines here, another imaginary lines here. So my hyperbola should look like this. Because it should be asymptotic. It shouldn't be beyond this line. Okay, so assuming my drawing is perfect. So according to the definition again, a hyperbola is a set of points at which, if you pick a point from that hyperbola, the absolute difference of the distance from a point to a focus and from a point to another focus is actually constant. Actually, that constant is measured the same as with the length of the major axis. So let's say, for example, I think my drawing is not perfect, but let me assume that it's really a perfect drawing. So let's say this is my center here. Center is at the origin. So let's assume, for example, I pick a point from the hyperbola. Let's say this is a point xy. Okay. Observe that if my center is at the origin 0, 0, again, the distance from the center to the focus, to one of the foci, is actually measured as c. So therefore, if here from here is measured as c, so then this point is c0, and this point is negative c0. Get it? Okay. If you take the distance here, and here to there, oh, I'm sorry, should be there. So let's say P to P1 minus P to F2 should be the measure of the line segment connecting the major axis. So let's assume, for example, that the line segment connecting the point P to F1 is quite larger compared to F2, although this is actually shorter in my illustration. So let's assume this is the point is taken here. So the larger line segment is actually from point to F1 compared to point to F2. So I don't have to take the absolute anymore because it's actually positive already. Assuming this is actually quite larger compared to this. So if I take the distance formula, I would have x minus c squared plus y minus 0, so that's squared, minus the square root of what is x minus, this is negative c, so it should be positive c here, plus y squared equals 2a. Okay, now, so we have derived the equation for the hyperbola provided that your center is at 0, 0 and it's oriented horizontally. So what happens if it's oriented vertically with the same center at 0, 0? So basically, instead of this hyperbola, it becomes like this. So technically, they only interchange the location. Like the major axis is now parallel to the y-axis and the minor axis parallel to the vertical axis. I'm sorry, the minor axis is parallel now to the x-axis. So what we have earlier is this one. So if in the case for the hyperbola with this, you just have to interchange the location. You do the same manipulation. I'm not gonna discuss that one anymore because it's the same manipulation, it's the same process. But if you have question, you can comment down there on how to get that. But you can get this instead. So it's just interchanging the x and y. Please. That's it. Now another question. You get this one as the hyperbola oriented horizontally and the hyperbola oriented vertically. What happen if, yeah, they're both oriented horizontal or vertical, but the center is not anymore on the origin. It's actually, let's say for example, in general at point Mn. Say we have the hyperbola this way. So our center is somewhere here. Let's say this is Mn. So we used to have a center here at the origin, and our hyperbola, we pick xy here. In this case, our center now is Mn. So if we pick a point here, let's say x bar, y bar, technically it's different from the xy point when the center is at the origin. So your x bar will now be x minus m. Your y bar will now be y minus n. Therefore, if it's oriented horizontally, when the center is at mn, you just replace that by x minus m squared over a squared minus y minus n squared over b squared equals 1. Same with this, you have y minus n squared over a squared minus x minus m squared over a squared equals 1. That's it. Okay, so let's consider an example here. So we have the equation 4x squared minus 9y squared minus 8x plus 36 minus 68 equals 0. So how will I know this is a hyperbola? Okay, let's double check again. Last time, what we can identify if the equation is a parabola if one of the two variables, x and y, one of them should bear the highest degree of 2, the other one should have the highest degree of 1. On the ellipse, you have to check that both of the variables, the x and y, should have a highest degree of 2. Both of them should be positive. In this case, you have to check that both of them has the highest degree of 2, but they have different signs. So one is positive and the other one is negative. In this case, the highest degree, xy, this is positive, this is negative, so you're pretty sure this is hyperbola. And as well as, you're pretty sure that since in this case, y is negative, so your hyperbola is oriented horizontally. Okay, so you have, in order for you to get the, so if given with these equations, you are asked to find the components of the hyperbola and you are going to plot the graph of this, you are going to rearrange this first because it's actually written in a general form. So you convert this into standard form. So you group the x and you factor them out. So 4x squared minus 2x minus 9 y squared minus 4y equals 68. So your next goal is to convert this term into a perfect square. So we can recall our knowledge or our skills back in elementary algebra that if I add here, I can add here this 1. So if this x squared minus 2x, if I add this by 1, I'll get x minus 1 squared. Same with this, if y squared minus 4y, if I add this by 4, I'll get y minus 2 quantity squared. So I have here x squared minus 2x. I will add this by 1. So technically, I'm just adding this by 4 because I can multiply this by 4 outside. So I will add also here by 4. So this is 9y squared minus 4y. So I will add this by 4. So technically, I'm adding 36, 9 times 4. So but this is negative, so I'll add this by negative 36. Okay, so I'll have 4x minus 1 quantity squared minus 9 y minus 2 quantity squared. So I shall get this a total of 36. So what we have earlier is that the equation, the general equation, should have 1 on the right side. So I will simplify this to make it this 1. So I will divide this by 36. So I also divide the other side by 36. So I will finally have x minus 1 squared over, so this is 9, so 3 squared minus y minus 2, this is 4, so I will have 2 squared equals 1. So this is now my A, this is now my B. So my A is 3, my B is 2. What does this equation imply? My center now is at 1, 2. how to get the C? So my C here is C squared equals A squared plus B squared. So I have 9 plus 4. So I shall get 13. So my C is square root of 13. So I took the positive because it's actually a measure of the distance. So my vertex is A units away from the center. So that's 3 units away from the center, since this is oriented horizontally, so it should be right and left. So my vertex 1 is 3 units from this. We have 4, 2. My vertex 2 is 3 units to the left, so that's negative 2, 2. Okay, my focus 1 is square root of 13, so I have 1 plus square root of 13, 2. My other focus is negative. That's it. My co-vertex is 2 units on top of the center, so that's 1, 4, and 2 units below from the center, so that's 1, 0. Okay, so how do I plot this? So my center is 1, 2, so that's somewhere here. My vertices is 4, 2, somewhere here, negative 2, 2, somewhere here. So this is now my major axis. So my co-vertices are 1, 4, so that's 3, 4, and 1, 0, so this is now my minor axis. So somewhere here is my focus. So anyway, what's important here is to create your imaginary rectangle. So and you form these diagonal lines. Oh, I'm sorry. Should be passing through the center. So this is your center. Because the center is the intersection of the major and the minor axis, as well as the intersection of the 2 diagonal lines. So this is now my vertex, so my hyperbola should be asymptotic to these lines. That's it. Okay, so let's consider another example here. Suppose that the major axis of the hyperbola is parallel to the x-axis with 6, 2 as one of the vertices and is 3 units from the right wing of the center. And one of the foci is negative 2, 2. Find the equation of the hyperbola. Okay, so this is pretty obvious when we say the major axis is parallel to the x-axis. So when the major axis is parallel to the x-axis, your hyperbola is oriented horizontally because your major axis is horizontal. So let's plot this first. Suppose somewhere here is your 6, 2. So therefore this is your vertex. So from the right side of the center is this. So therefore you can find the center here. The center is 3 units away. So if this is 6, 2, you're pretty sure that this is 3, 2. Because 3 units from 6, 2 is 3, 2. Negative 2, 2 is where the foci lies. The focus lies. So that's 3 units away. So therefore your A is 3. Your C, which is negative 2, 2, so that's technically 3. So that's 5 units away from, the focus is 5 units away from the center. So my C is 5. Therefore my B squared is 5 squared minus 3 squared, so that's 25 minus 9, that's 16. Therefore, B is 4. And since this is oriented horizontal, so the equation that I will be following is this. So I got the center already. I have the information of the A. I have the information of the B. So therefore, I have x minus 3. So let me double check again. Yeah, I'm right. So squared over 9 minus y minus 2 over 16 equals 1. So whichever of these, you can either simplify these to get the general equation, or you just stop with this. That's already correct. Okay, so if you have a question, you can comment down there. That's it. Okay, so let's consider another example here. Find the equation of the hyperbola with vertices 1, 4, and 1, negative 2. And the center with the co-vertices and the vertex form an isosceles triangle. So let's plot this first in order for us to imagine how our hyperbola look like. So this is the graph here. We have 1, 1, 2, 3, 4. So basically, this is where the vertex lies. The second vertex lies here. 1, negative 2. Okay, so basically, since this is the vertex, if you connect a line segment, you're pretty sure that the hyperbola is oriented vertically because the line segment connecting the two vertices is vertical. So the midpoint of these two lines, of course, will be the center. So what's the midpoint of these two points here? So that's from 1, negative 2. So that's 0 here. That's 2 here. So I guess it's 1, 1. 1, 1 to 1, 4, the distance is 3. 1, 1 to 1, negative 2, the distance is 3. So you're pretty sure that your center is 1, 1. And of course, the center, the vertex, and the co-vertex form isosceles triangle. So let's say this is the co-vertex here. They form isosceles triangle. Okay, let's recall back in our geometry class. I guess you were third year high school that time. Isosceles triangle is when two sides of the triangle are congruent. So these two here is equal. So if the measure of these is 3 units, because the distance from 1, 1 to 1, 4 is 3. So you're pretty sure that the distance as well with this is also 3 units. So 3 units from 1, 1 to the right is actually 4, 1. So therefore, this is the co-vertex. Another co-vertex is 3 units from to the left. That's negative 2, 1. Okay. Hence, so this is the vertex. Hence, our A and our B are equal, 3 units. So solving for C, so that's 9 plus 9, that's 18. So our C here is 3 square root of 2. So somewhere here, somewhere here. Oh, I'm sorry. The focus is somewhere here, somewhere here. Okay, so if we form an imaginary rectangle from these points, so I'm sorry, I'm not good in drawing this. So it should be like that. Should be like this. Okay, so this is our hyperbola. Your hyperbola should be asymptotic to this line. Okay, so solving for the equation, so since that's oriented vertically, so our equation should be like this. A squared equals 1. So our center is 1. So our B is 3 squared, so 9 minus y minus 1 squared over 9 equals 1. Okay, so the next example is find the equation of the hyperbola with center at the origin, having one of the vertices and foci lie on points 4, 0 and 6, 0 respectively. So I'm not going to answer on this problem. What I want you to do is you answer your own, and you can comment down there on your answers regarding on this question. Okay, we're done with the study of hyperbola. So thank you so much for listening. So what we've done so far is we're done with the circle as a conic, parabola as a conic, ellipse as a conic, and the hyperbola as a conic. So we're done with the conic sections. So thank you so much for listening, and we'll be discussing more about pre-calculus series. That's all. If you have a question, you can comment down there, and please subscribe on the subscribe button below this video. Thank you.